Every now and then, there comes a research paper which really gets you thinking. This Meta's latest paper is one of them. This paper basically suggests, in very simple words, that training LLMs to predict multiple future tokens at once results in higher sample efficiency. If you think about it, it actually makes sense because we humans over the years have condensed their most ingenious undertakings, surprising findings, and beautiful productions into form of books. LLMs trained on all of these books are able to extract impressive amount of world's knowledge as well as basic reasoning capabilities by implementing a simple yet powerful unsupervised learning task, which is next token prediction. Despite the recent wave of impressive achievements, next token prediction remains an inefficient way of acquiring knowledge, world knowledge, and reasoning capabilities. More precisely, teacher forcing with next token prediction latches on local patterns and overlooks hard decisions. That is why it remains a fact that state of the art next token predictors call for order of magnitude more data than human children to arrive at the same level of fluency. And there are already a lot of manifest of that thing. For example, look at this diagram. On the top one, during training, the model predicts four future tokens at once by means of a shared trunk and four dedicated output heads. During inference, the researchers are employing only the next token output head. Optionally, the other three heads may be used to speed up inference time. How good is that? And if you look at this diagram, similar things are happening, but one thing I missed to mention in this one in the bottom, multi-token predictions improves pass at 1 on the MBPP code task, which is shown here. How good is that? And that is why the model size increases. Error bars are confidence intervals of 90% computed with bootstrapping over dataset sample, by the way. So in this paper, again, if I go back here, the researchers are arguing that training LLMs to predict multiple tokens at once will drive these models towards better sample efficiency. So if you look at this figure, multi-token prediction is instructing the LLM to predict the n future tokens from each position in the training corpora all at once and in parallel. While multi-token prediction has been studied in various previous papers and I have covered few of them, this work is something different because it makes it so workable, and I'm more than sure this is going to be implemented very soon because the thing which is it is proposing is a simple multi-token prediction architecture with no train time or memory overhead. They have also provisioned experimental evidence that this training paradigm is beneficial at scale, with models up to 13 billion parameters solving around 15% more code problems on average. Multi-token prediction enables self-speculative decoding, making models up to 3 times faster at inference time across a wide range of batch sizes. While cost-free and simple multi-token prediction is an effective modification to train stronger and faster transformer models, I think this work spurs interest in novel auxiliary losses for LLMs well beyond next token prediction to improve the performance, coherence, and reasoning abilities of these fascinating models. So, the overall architecture is very interesting. It consists of a common trunk that processes the input sequence to generate a latent representation of the observed context. On top of that, multiple output heads are each responsible for predicting a different future token simultaneously and independently. Instead of predicting just the next token, the model predicts several future tokens from each position in the input sequence. Each output head makes its prediction independently based on the shared context provided by the trunk. During training, the model is optimized for predicting each of the future tokens independently. This approach trains the model to improve its prediction by considering multiple future outcomes at each step. The predictions are generated in parallel across the multiple heads, so this doesn't add any computational overhead. At inference time, the model can use the trained output heads to generate multiple tokens at once, speeding up the process. And that is the whole idea behind it, to speed up this process, because even in today's world, when you are using the model, we often see that they lag sometime when there is a huge corpora of data to go through. And I think that is where we will see a lot of implementation by different companies, and I'm sure many companies are going to take this away from Meta. So really awesome work by Meta, because I think in future I would also like to better understand how to automatically choose n multi-token prediction losses. And Meta has also mentioned in this paper that the one possibility to do so is to use loss scales and balancing. Also, optimal vocabulary sizes for multi-token predictions are likely different from those for next token predictions, and tuning them could lead to better results as well as improved trade-offs between compressed sequence length and compute per byte expenses. So it will be really good to see some implementation of this paper, as I think this is going to be a real hit in the future. Let me know what do you think. I will drop the link to this paper in video's description. If you like the content, please consider subscribing to the channel. And if you're already subscribed, then please share it among your network, as it helps a lot. Thanks for watching.